Assalamualaikum and hello everyone. My name is Ahmad Farhan bin Ru Azam.
Hello, my name is Wan Amirul Kushairi.
Hello, my name is Muhammad Huzami Afiq.
Hello, my name is Ahmad Shaki.
My name is Muhammad Solihin.
My name is Johan Rizki.
My name is Muhammad Mizan bin Muhammad Zahid.
We are from Group 8. We discuss about the Group Project 1, Dynamical System.
Based on our Group Project 1 in Dynamical System is Rahawis criterion. We choose our topic is compensation of communication delay in a cooperative ACC system. What is ACC system? The system is relay on a real-time communication between vehicles to enable coordinates, driving behavior and improve traffic flow. Okay. However, communication delay significantly impact the performance and effectiveness of this system. For example, if a vehicle A predict that vehicle B is likely decelerate due to an obstacle based on its previous behavior, is automatically initiate braking to maintain the safe following distance. This prediction and compensation process help mitigate the impact of communication delay, ensuring that the platform remains safe and responsive. In summary, the compensation of communication delay is a critical aspect in the development and implementation of cooperative ACC system on vehicle by addressing communication protocol if it possible to mitigate the negative effect of delay. How about what do you think about problem statement?
Okay, my problem statement is as four. First is the problem addressed in the study is revolves around the impact of communication delay on stability and the performance of cooperative adaptive cruise control, which is CACC system. Okay, second is communication delay refers to the time lag between sending and receiving information through communication system. The third one is it has been established that such delay can significantly higher than effectiveness of CAC system, resulting in poor performance, particularly in the real world scenarios with extreme communication delay. Lastly is the focus of this study is modeling and control of a cooperative electric cruise control system, CACC system.
So, based on your problem statement, I think the objective of this study is to enhance the stability of the CACC system by mitigating the adverse effect caused by communication delay. And second objective is to understand the relationship between communication delays and system stability and developing strategies to improve performance under various traffic conditions. And the last one is to contribute to the development of reliable and robust CACC system that can operate efficiently even in the presence of communication delays.
Okay, next we continue with methodology.
Okay, so before we understand the Rothschild stability criterion, there are three types of system, which is the stable system, where all routes of the system is lie on the left side of the S-plane. The second one is unstable system, which is the all routes lie on the right side of the S-plane, and the third one is a marginally stable, which all routes lies on the imaginary axis of the S-plane. So the criterion states that any system can be stable if and only if all routes of the first column have the same sign. If it doesn't, have the same sign, or we can say that there is a sign change, then the number of sign change in the first column is equal to the number of routes in the characteristic equation in the right half, or the unstable of the S-plane, which is equal to the number of routes with the real parts. We can consider the characteristic equation. So we can say that there are some necessary conditions to make the system stable, which is all of the coefficient of the equation should have the same sign, and there should be no missing term. there's no assurance that we can say that the system is stable or not by referring to the properties here. To do this, we need to apply the Roth-Hurwitz criterion to assess the system stability. The system is said to be unstable if the predetermined condition is not met. So there are few advantages from this criterion, which is we can find the stability of the system without solving the equation. We can determine the relative stability of the system. We can determine the range of K for the stability, and we can also determine the point of intersection for root locus with imaginary axis. So there are few limitations, which is the criterion is only applicable in linear system. It does not provide exact location for the poles of the right and half of the S-plane, and in the case of characteristic equation, it is only valid for the ring coefficient. So there are 4 steps for this Roth-Hurwitz criterion, stability criterion. The first one is to arrange all the coefficient of the double equation in 2 rows. Then from these 2 rows, we will form the 3rd row. Now we shall form the 4th row by using 2nd and 3rd row. Then we can continue this procedure from forming a new row. So let's continue with the solution. Yes, the solution. What do you think?
I actually think that we can solve the problem by using transfer function method. So as we can see from the slide, we have Q, V and A equation. So whereas AI is the actual acceleration of the vehicle, and delta I represents the vehicle actuator delay, and the third equation, which got the tau there, is represent the driveline dynamic, where tau is a time constant. Consequently, the transfer function GS from desired acceleration UI, two quotient read as this formula, this GVNA. So for the next slide, on the next slide we have the first equation, where SC is the Laplace variable, UI and QI denote as Laplace transform of UI and QI respectively. So for the next equation is actually where SC is Laplace variable, UI and QI denote as Laplace transform of UI and QIT respectively. So on the next slide, for the first equation, we can see where SC is the Laplace variable, UIS and QIS denote as the Laplace transform of UIT and QIT. So for the next equation, which is the second equation, a constant time gap spacing policy, improved string stability and desired inter-vehicle distance DRI between vehicle and I involve a standstill distance RI and a velocity dependent path. So the next step is the fourth equation, which actually is the time gap case for homogeneous CACC string, actual inter-vehicle distance DI. So we continue with the next equation, which is explains about to realize the vehicle following objective, the inter-vehicle distance error EI, also defined as the equation. So for the next equation, is when the controller is adopted, where a pre-compensator with input epsilon I is introduced. For the next equation is to stabilize the aerodynamics, the control law for epsilon I. For the sixth equation is to stabilize the aerodynamics, the control law for epsilon I. For the seventh equation, it states about where Kp and Kd represent the controller parameter, Ui minus 1, Ce is received desired acceleration of preceding vehicle. And for the eighth equation, which have the H, K and D, explains about without loss of generality, we choose Ri, Li equal to 0 when analyzing stability and string stability. That's why the CACC system of homogeneous interconnected vehicles is string stable. And the last one we can see from the slide is considering, for instance, the desired acceleration, the transfer function for SORGS from UI-1 to UI. As you can see from the slide, here we have the block sim of the one vehicle loop, a CACC system. here we introduce the string stability of this one vehicle look ahead CACC system, adopting the so-called performance-oriented approach, which is characterized by amplification in upstream direction of the signal of interest. So we can go to the problem solution, which actually use the dynamical system approach. So Johan, do you mind to explain?
So as for the example and solution, I already provide the solution. So basically for the solution, firstly we have to provide an few equation that is fulfill and satisfy the form of x dot is equal to fx. So I found three equations related to our research, such that q dot is equal to v, v dot is equal to a, and a dot is equal to negative 1 over tau a plus 1 over tau ui t minus theta a, such that q is equal to distance, v is velocity, a is actual acceleration, and ui is desired acceleration. So for the first step, for Rhodowitz method, we need to find the equilibrium point or equilibrium point, such that firstly we need to find q dot equal to 0, so we will get v is equal to 0. Then find for v dot equal to 0, and then we're going to get a is equal to 0, and lastly a dot is equal to 0. Then we will get 1 over tau ui t minus theta a is equal to 0. So based on the paper that I have followed, if the condition if t is less than theta a, such that uit is gonna be 0. Then if t is more than theta a, then uit will be not equal to 0. So based on the condition, I already get the equilibrium point or the critical point is 0, 0, 0, referring to the coordinate of q, v, and a. So for the next step, we're going to find the Jacobian matrix, and then we're going to substitute the equilibrium point into the Jacobian matrix. Then the diagonal for the Jacobian matrix, after we substitute the values, we're going to subtract it with lambda to find the eigenvalue. So after we finish that step, we're going to find the determinants for the Jacobian, and we're going to equal it to 0. Then we're going to get the characteristic equation, which is lambda cube plus lambda squared over tau is equal to 0. So based on Rhodowitz criterion, we compare the characteristic equation that we already get with the general form characteristic equation for Rhodowitz, such that we're going to get a1 is equal to 1 over tau, a2 is equal to 0, and a3 is equal to 0. So after we already get the value of or the function of a1, a2, and a3, we're going to find the matrices for Hj, such that we get a1, a2, a3. So we're going to have three types of matrices, which is h1, h2, and h3. So for h1 is equal to matrix of a1, which is 1 over tau, and the determinant is when we calculate is greater than 0. For h2, the form of the matrices is a1, 1, 0, and a2. Then we substitute the value of a1 and a2. Then if we calculate the determinant of h2, we're going to get 0. And lastly, for h3, this is the form. It's a1, 1, 0, a3, a2, a1, 0, 0, and a3. So we calculate the determinant, we're going to also get the determinant of h3 is equal to 0. So based on the Rhodowitz criterion, the determinant of Hj for the stable condition should be greater than 0. But in this case, we only get the determinant for Hj such that H1 only equal to more than 0. But for the other determinant, we only get equal to 0. So since based on the condition, we can conclude that the system is unstable. So, what can you say about our discussion with this?
So, to conclude our discussion today, it is actually highlight the significance of CACC system, also the challenge of communication delays, and also compensation strategies and the importance of stability analysis. So it's actually in this discussion it emphasizes the goal of ensuring safe and stable driving behavior and present the purpose objective to contribute to the development of more robust CACC system throughout comprehensive stability analysis as have been done by Johan. So the problem statement focusing on the importance of the communication delays in CACC system identifies their negative effects and emphasize that the need to enhance the system stability by mitigating these negative delays. So the research will likely seek to provide a solution that improve the performance of the CACC system in real world scenario with varying levels of communication delays. The method Rod-Hawkins criteria actually allows us to determine the stability of a system by examining the sign and number of sign change in the first column of the rows array, and if all the signs are the same, the system is stable. So that's it. If there is a sign change, the system is unstable. So, and the research aims is to address the adverse effect of communication delays in CACC system by understanding the impact on system stability and developing strategies to improve performance. The goal is to contribute to the development of more reliable and robust CACC system that can operate efficiently under various traffic conditions, including scenarios with the communication delays. I think that is the conclusion for our discussion today.
So that's all from us. Thank you.
Thank you.
Bye.